So let's say we have some function f of x. So some function f of x. And we need to find the derivative of f of x. And I'm going to call that f prime of x. What's that equal to? Well, up until now, we would have said, oh, well, this is what we just learned. This is the limit as h goes to 0, h or delta x, they're really just the same thing. They just represent the same idea, of f of x plus, oops, I almost wrote delta x there, f of x plus h minus f of x divided by h. Again, h means the same thing as delta x in this case. It's really just a matter of notation. But this is kind of a lengthy formula for finding a derivative, right? I mean, if we have a really complex function, that could be pretty hard to work out. So there are a series of methods for finding derivatives that I'm going to teach. I won't be proving any of them yet, but I think it's really important to have an understanding of their use and how you can apply them when finding derivatives. First of all, I'm going to introduce a series of kind of general rules for derivative taking, and then I'm going to get into something called the power rule. All right, so the first rule I want to introduce is this rule of addition. If we have some function f of x, which is equal to a series of kind of, I'm going to say, easily differentiable functions, which means functions that are easy to take the derivative of, but might be hard to kind of, if they're all together, take, like, just plug into the derivative formula that we got, which is going to be g of x plus h of x plus, however many we want, however many functions that we can break down. I'm just going to say however many functions for now, right? So by this I mean, let's say we have f of x is equal to, this is going to be our example, sine of x plus x squared. Now, we don't really know how to take the derivative of sine of x yet, but that doesn't matter for this video. What we can do here is say that f prime of x is equal to just the sums of each derivative. So g prime of x plus h prime of x. Okay, or in our example, we could say that this goes to f prime of x, which is equal to, now how are we going to represent the derivative of sine of x? Because we don't really know that yet, right? I haven't taught you that. So I'm just going to say, I'm going to use this other notation for derivatives, dx of sine of x plus, we just solved for the derivative of 2x. We have that down. I just said it, the derivative of x squared. That's 2x. And this would be the derivative of our formula sine of x plus x squared. It's very simple. You just add the derivatives of each respective function to find the derivative of the function that's equal to the sums of those functions. So if f of x equals g of x plus h of x, f prime of x is going to be equal to g prime of x plus h prime of x. It's pretty simple. Then there's one other rule which I think will also make a bit of sense. So the next rule is one of multiplication, or rather coefficients. In this case, we have f of x is equal to, let's say, we'll just use some constant c. It's just a constant. You could also call it a coefficient. That could be equal to 5 or 3 or 2 or 1.5 or pi or just some constant times another function that we know, g of x. And you can think of this entire thing as a function. Yes, it's one function, f of x, but we separate it basically into functions that we can easily take the derivatives of. So we have f of x equals some constant times g of x. What is f prime of x going to be? Well, actually, since c is a constant, this is just going to be c times g prime of x. You can imagine when we're taking the derivative with respect to x of c times g of x, this c just kind of hops out. Just hops out so that it gets out of here and comes out here. So it becomes c times the derivative with respect to x of g of x. And this is the case. So what about an example? We have, let's say, f of x is equal to, what should we do for this one? How about 4x squared? All right, so we can just separate this 4 out. So if we're taking f prime of x, I'm going to use the interesting notation again. Again, you can just think of separating the 4 out, which you could just do in your head, but I'm going to do the derivative with respect to x of 4x squared. And that's going to have, we're going to have the 4 jump out. So that'll be equal to 4 times the derivative with respect to x of x squared. And this we know, we did this a couple videos ago, or perhaps last video. This we know to be 2x. This whole thing is 2x. So that will be just equal to 4 times the derivative with respect to x of x squared, which is 2x, or 8x. And you probably could have done that in your head, but I think it's useful to just break it down so that it's a little simpler. Let's try now tying these together. Let's say that we have the function f of x is equal to 5 times x squared plus, trying to choose a good function. What would be a good function for this? Plus, how about 3x? Now, you may say, oh, wait, we haven't done 3x before, but actually you have, and we'll get to that in a moment. So, what's f prime going to be? Well, first of all, we can break this into separate sections. F prime is going to be equal to, we can take the derivative of these sections separately, and then just add them up. So the derivative with respect to x of 5x squared plus the derivative with respect to x of 3x. All right, now let's solve the first one. This is going to be equal to, well, you know, we've seen this done. Just take the derivative of this x squared, 2x, or just, you know, you're carrying that 5 out of there. So 5 times the derivative of x squared, it's going to be 10x. And then we're adding this thing. What's the derivative of 3x? Think of the function. Think of the function y is equal to 3x, right? This is a linear equation. Y is equal to 3x. This is the equation of a line. A linear equation might not be the best word to use, but this is the equation of a line. And this here, that's our slope. That's our slope, right? In old algebra, it's just the coefficient on x, that's our slope. Just as the derivative is our slope. So our derivative for this is just going to be 3. And we'll learn how to compute that without any kind of intuitive understanding or using the formula in a moment. So this is going to be our final f prime of x. All right, now I want to get into the power rule. All right, so the power rule is just one of these methods for solving derivatives that is just really useful in doing things quickly. And it's actually, I'd say, the simplest of the bunch, and one that you'll use quite often. Maybe less so later on, but at least for now, you'll probably use it quite often. So the power rule simply states, if we have some function of x, you know, x is just a variable, just could be function of q, whatever, just some variable, is equal to that variable raised to some power, we're going to call it n. And we'll have an example so this makes more sense. So that could be x squared, x to the 5th, x to the 1008th power. It doesn't matter. That's how many times x multiplies by itself. Now, the power rule states that f prime of x is going to be equal to that power times x to the n minus 1, to that power minus 1. So you can just imagine that when we're going here, we're just flipping that n over and back of the x to become a coefficient, and then taking 1 away. So let's clarify that with an example. So let's say f of x is equal to x cubed, or how about something more exciting, x to the 30th power. We'd say that f prime of x is equal to, right, we carry this down, 30 times x to the, right, we take a 1 away, so we're taking 1 away. So we're taking 1 away, x to the 29th power. What about something more familiar? What about f of x is equal to x squared? We carry the 2 down. F prime of x is equal to 2x to the 2 minus 1, right? We're taking that 1 away, which is just equal to 1. X to the first power is just x, so that's going to be equal to 2x. Just like we found before using the formula. Now there's one more example I'd like to do just to sum all of these up. All right, now for one last example. So we're going to have some function of x, and that's going to be equal to x to the 5th minus 3x squared plus 20x minus 32. Now, how about 3200? Ooh, okay. How are we going to find the derivative of this? Well, let's break it down. Remember, we can separate this into separate parts. Now, if you'd like to try this on your own, go ahead, but I'm going to continue going if you'd like to pause the video. So first, let's find the derivative of x to the 5th. Well, that's going to be, we carry that power down to become a coefficient, 5x to the 5 minus 1, minus, wait, should we do minus though? Let's keep with adding, because we know about adding. This is, look, we have a coefficient, -3 on here, plus, remember, we can take that out of the derivative, so we're doing -3 times the derivative of this thing, x squared. We know the derivative of that, and we can use a power rule. It's going to be the 2x. All right, what's the derivative of 20x? Well, that's just a line, right? Or you could use a power rule. We could say there's a 1 up here, and we could do 20 times x to the 1 minus 1. You'll see that turns out to be the same thing as it would otherwise. Now, what about this constant here? Well, you can think of this in terms of an actual graph, where we have some line, we have some graph here. If our function was just equal to some value, -32, which is going to be down here somewhere, but if it was just equal to some constant, I'm just going to say a positive constant here, this is just a flat line. The slope here is 0. The derivative is 0. Now, you could also use a power rule, however, saying that this is the same as 3200 or -3200 times x to the 0th power times 1, right? So we bring 0 over. We're multiplying by 0, so no matter what happens over here, it's just going to be plus 0, right? The derivative of a constant is 0. And that gives us our final answer, 5x to the 4th minus 6x plus 20x to the 0th, which is just 20. All right. I think that was a lot of fun. Thanks for watching.